Melting points, background. In this webcast, we will discuss what melting points are, what can affect them, and how to determine the melting or freezing point of a mixture using a phase diagram. For a quick review from general chemistry, physical properties can be identified by observing a sample. While physically watching a sample, the identity of the sample does not change, and as a result, the physical properties of that sample also do not change, making them characteristic of that compound. Examples of physical properties include the solubility of a compound in some solvent, the boiling point of that compound, the color of that compound, and the melting point of that compound. For example, pure gold is always yellow. The color is characteristic of gold. Melting point is the temperature at which there is a phase change from solid to liquid. An example of this would be ice turning into liquid water. Here on the right, we have a phase diagram. Remember that a phase diagram shows how the phases of, in this case, a pure compound, changes as the temperature changes. Here on the x-axis, we have the amount of heat added to our sample. Whereas we go from left to right, we add more heat. On the y-axis, we have the temperature of our sample. Whereas we go from the bottom to the top, we have an increase in temperature. We start here in the bottom left with a solid at some temperature. As we add heat to it, the temperature of that solid increases. This continues until we reach the melting point. At the melting point, we continue to add heat, but the temperature does not change. This is because all the energy from the heat is being used to convert the solid into a liquid, until all of our sample has melted, turned into a liquid, at which point the heat can then be used to continue increasing the temperature of the sample. At the melting point, at this plateau area of the phase diagram, both liquid and solid exist in equilibrium. By adding enough heat to a sample, we can drive the equilibrium to complete liquid, or by removing enough heat, we can drive the equilibrium to complete solid. For a pure compound, the melting point is actually a melting range. The compound will melt over a narrow temperature range of about 1 to 2 degrees Celsius. If we have an impure compound that contains soluble impurities, notice how soluble is in red there, we'll come back to that in a moment, the melting point will be much lower and have a wider temperature range. This effect of soluble impurities on the melting point of a sample is called a melting point depression. As a result, melting points are an indicator of purity, where more impurities result in a larger melting point depression. If you know the melting point of a compound, and your sample of that compound does not match that melting point, that means your sample must be impure. The farther away your sample's melting point is from what the melting point should be, the more impure your sample is. Why do impurities cause this melting point depression? This has to do with the crystal lattice of the solid. Here on this slide, we see a number of turquoise circles arranged in a regular repeating pattern. Each of these circles represents one molecule. It takes energy to break this lattice up and convert these molecules from the solid phase to the liquid phase. Let's add an impurity into our crystal lattice and see what that does. Here on the right, I have the same crystal lattice, but I've added this yellow circle, which represents an impurity. Because this impurity is a different molecule than the rest of the solid, it disrupts the crystal lattice. It causes all of the other molecules to not fit together as well as they should. As a result, the crystal lattice is weaker, and it takes less energy to break it apart. The solid melts at a lower temperature. To show the effect that an impurity has on the melting point of a compound, we can use what is called a phase diagram. This slide is showing what is called a two-component phase diagram, where our mixture contains only two compounds, here labeled A and B. Along the y-axis, we have the temperature of the sample, where as we go from the bottom to the top, we increase in temperature. Along the x-axis, we have the mole fraction of our mixture, in this case specified as the mole fraction of compound B. The mole fraction is simply a ratio of the number of moles of a particular compound, in this case B, and the total moles of compounds in the mixture. For example, if in my mixture I have 1 mole of B and 1 mole of A, the mole fraction of this mixture is 1 mole of B over 2 total moles of compound to give me a mole fraction of 0.5. Mole fraction is essentially another way of writing percent. If I have a mixture that is 0.7 mole fraction of B, that means my mixture is 70% B. The reason we use mole fraction instead of percentage is because mole fraction is used in several mathematical equations. Okay, how do we interpret this phase diagram? This phase diagram has 4 regions. This yellow region at the top, these light blue regions on the sides, and this dark blue region down below. Each of these regions has been labeled with the phases of the compounds present at a particular mole fraction and at a particular temperature. If we take a mixture that is 0.2 mole fraction of B, we see that at 2 degrees, the mixture is completely liquid. However, if we take that mixture and cool it to be -1 degrees, we see that we have moved into a new region, where, as we can see from the label, we have solid A and a liquid mixture of A and B. Between these 2 regions is this black line here. This black line is called the liquidus line. The liquidus line shows us when we transition from a pure liquid mixture to where we begin to start seeing some solid. As you can see, as we go from the edges of this diagram towards the middle of this diagram, the temperature at which we go from liquid to solid decreases. If you look at where these liquidus lines intersect the left and the right edges of the phase diagram, we see that we are at 0 mole fraction of B here on the left, otherwise known as pure A, and a mole fraction of B on the right of 1, in other words, pure B. Where the liquidus line intersects the edges of the graph shows where the pure compounds melt. In this case, pure A melts at 1 degree Celsius, whereas pure B melts at somewhere around 0 degrees Celsius. As we mix A and B together, we see that the transition temperature between liquid and solid decreases until we reach this point in the middle. This point is called a eutectic point. A eutectic mixture is the ratio of compounds that will melt at a lower temperature than any other ratio of compounds. The eutectic point itself is the point where the eutectic mixture, liquid phase, meets the eutectic mixture, solid phase. In other words, it is where a eutectic mixture transitions from liquid to solid. Here in the winter in Illinois, it snows. And when it snows, that snow can melt and then freeze into ice, which is quite dangerous. To try and prevent this, we salt the roads. The salt on the roads dissolves in the water on the roads that comes from melting snow. You can see what effect that has on the freezing point of water in this phase diagram. We see that in this phase diagram, our x-axis is the percent of sodium chloride in our mixture, in this case by weight, which means that at 0% sodium chloride we have pure water, and we know that pure water freezes at 0 degrees C. As we add more and more salt, the freezing point of our mixture, our salt water, decreases until at a certain point it reaches -21 degrees Celsius. What this means is that by adding salt to the roads, we cause the water to remain water longer and not turn into ice. The reason this works is because salt is soluble in water. In order for a compound to disrupt the crystal lattice of water as it tries to freeze, the compound has to dissolve in water. This is why we can't just sand the roads. Sand is insoluble in water. So while sand provides traction, it does not help prevent water from freezing. Here is a phase diagram where acetic acid is mixed with water. As you can see, our x-axis is the mole fraction of water in our mixture, and the y-axis is the temperature of our mixture. We see the liquidus line up top, and also what is called the solidus line down below. Remember that the liquidus line is where we transition from complete liquid to seeing some solid. The solidus line is the opposite, is where we transition from solid to seeing some liquid. Let's analyze this phase diagram. First, what are the melting points of pure acetic acid and pure water? If you look on the left, where we have a mole fraction of water of 0, in other words, pure acetic acid, we see that the liquidus line intercepts the y-axis at about 17 degrees Celsius. Whereas on the other side, where we have a mole fraction of water of 1, pure water, we have a melting point of about 0 degrees Celsius. And if we could zoom in even further, we can get some exact values for these melting points. Okay, so our eyeball guesses were pretty close to the actual values. Now let's see if we can identify a eutectic mixture of water and acetic acid. We know that a eutectic mixture creates a eutectic point, and a eutectic point is the place on the diagram that has the lowest melting point. We see here on the diagram that the lowest melting point is right here. And the mole fraction of water at that point is about 0.7. Therefore, a mixture that is 70% water and 30% acetic acid is a eutectic mixture. Now let us use a phase diagram to show what happens if we take a sample of acetic acid and water and begin to freeze it. In this example, we have a mixture that is a mole fraction of 0.9 H2O, and it starts at 20 degrees Celsius. What happens as we cool? First, let's find the mole fraction on the x-axis. Here we go, 0.9 of water, and now let's find the relevant temperature. 20 degrees Celsius. So we start here on the phase diagram. Let's start cooling it. Let's lower the temperature, lower the temperature. Eventually, we reach the liquidus line. At the liquidus line, we begin to freeze our mixture, but not the entire mixture begins to freeze. At this point, only water begins to freeze. So as we take this mixture and begin freezing it, the solid we make is pure water. What's the consequence of this on the mole fraction of the liquid mixture left behind? Well, if we are taking water and only water from the liquid mixture and turning it into a solid, then the mole fraction of water remaining in the liquid must decrease. In other words, we move towards the left on this phase diagram. As we freeze more and more water, the liquid contains less and less water. So our mole fraction of water has to decrease, and this continues until we reach the eutectic point. At the eutectic point, we have a eutectic mixture. What's special about a eutectic mixture is that the solid that forms when a eutectic mixture freezes is the same composition as the liquid it started with. So, at this point, we have only solid water and a eutectic mixture in the liquid. If we continue cooling, the liquid continues to freeze, only now, because we are a eutectic mixture, both water and acetic acid begin freezing, turning into a solid. The solid that forms as a result of freezing a eutectic mixture is a eutectic mixture. So in this case, if our liquid is 70% water, then the solid that forms as a result of freezing the mixture is also 70% water. We continue cooling until all of the liquid is frozen, then our new solid composition has to be the same as what we started with. Hopefully that makes sense. If we take a sample that is 90% water and we freeze all of it, the solid has to also be 90% water. If we continue cooling, the temperature simply continues to fall. Let's walk through that one more time. We started with a mixture at a particular mole fraction at a particular temperature. We began to cool it down until we hit the liquidus line. When we hit the liquidus line, the water and only the water began to freeze. As a result, the mole fraction of water in the liquid left behind decreases and continues to decrease until we reach a eutectic mixture. Once the liquid left behind is a eutectic mixture, both water and acetic acid begin to freeze simultaneously, and they freeze in a eutectic ratio. This continues until the entire sample is frozen, at which point the temperature simply falls as we continue cooling the sample. This was an example of freezing. You can imagine an example of melting, which is identical except just going in the opposite direction. For example, we can start down here in the completely solid region, begin heating, and then once we hit the solidus line, we begin to melt. The mixture melts until we have only solid water, at which point, as the pure remaining solid water melts, the mole fraction of the liquid phase increases in water until everything has melted, and then we simply heat the completely liquid mixture. That brings us to the end of this webcast. To recap, the melting point of a compound is characteristic of that compound. No matter how many times you melt a sample of pure water, it will always melt at 0 degrees Celsius. Impurities can affect the melting point of a compound. Soluble impurities lower the melting point of a compound by disrupting the crystal lattice. Remember, this is only for soluble impurities. Insoluble impurities do not affect the melting point of a compound. Phase diagrams show what phase a mixture of compounds is in based on the mole ratio of the compounds in the mixture and the mixture's temperature. In a phase diagram, the curves, for example the liquidus line, and lines, for example the solidus line, between regions in the phase diagram show the beginning of transition between phases. These curves and lines are where you start to freeze and or start to melt, depending on which direction you're going.